Okay, so we are starting, we're finishing 9.3. So now we're really going to get into, I shouldn't say 9.3, but sampling means, okay? So we've done sampling distributions where we talked about what are the parameters, what are the statistics. We talked about low bias, high bias, low variability, high variability. And we talked about, different parameters, different statistics. In section 2, we talked about P and P hat and how to find the standard deviation and how to prove normality and how to prove that we can use standard deviation. Okay. So, if on the other hand, so yesterday we talked about categorical data, we talked about P hats. Now, right now what we're going to talk about, if on the other hand we have quantitative data, then we can use sample means. Okay, so for categorical data, we use proportions. For quantitative data, we're going to use sample means. Now, when you go and look at this example that I have on the next page, you're really going to notice that this kind of looks like what we did in the first section. You're absolutely right. But now we're going to really talk about our means, okay? I can take this off. Okay. So, we have a sample of 100 seniors' GPAs. And yes, we have talked about this, and you guys are still floored that these GPAs can exist. I know. It is kind of weird. So these 100 seniors make up one possible what? Yes, this is just one sample. The more samples we take, the more data we collect. That is the law of large numbers, the closer we get to the population mu. Do you guys know where you're at? Got it. Okay. So the sample mean, what symbol do we use for the sample mean? X bar. Okay. And what characteristic? Oh my gosh. What symbol do we use for standard deviation? Okay. And what is our parameter? If our sample mean is X bar, what's our parameter? Mu. And that's not to be confused with a cow moo. It's just mu. Okay. Oh, you guys can't see that. There we go. Okay, so mu is our parameter. And X bar, our statistic, is the mean GPA of a senior in Florida in an SRS size of 100. So depending on the sample we take, it depends on what our GPA is. To calculate the value of mu, we find the mean of our sample, which is X bar. If we pick different samples, then the value of our statistic, X bar, changes. Please notice now they had P1, P2, P3, but notice that now it's X1, X2, it's the mean of 1, the mean of 2. You can see the samples. If that confuses you, just go like this. I'm fine with that, okay? Because these are X bars. So sample 1 has a mean of 2.5470. Sample 10 has a mean of 2.5667. So we've taken 10 samples of 100. We pulled all their GPAs. We've added them together and divided by 100, and that's the GPA we got. Okay? Is everyone with me so far? Okay, just like we talked about yesterday when we graphed P hat, that was a sampling model. If I graph values of X bar for all possible samples of size 100, then I have constructed a sampling model. So yesterday we talked about if I graph all the values of P hat, right, for all the possible samples of 100, then I constructed a sample model. So if you're it doesn't matter. Do you guys see? It's still a sampling model when you're graphing all those samples. Remember that each X bar value is a mean. Means are less variable than individual observations, because if we are looking only at means, then we don't see any extreme values, only average values. We won't see GPAs that are very low or very high, only average GPA. So what that means is we're looking at the sample mean. We're not looking at individual means. We're taking individual means, finding the average of those 100, and we're getting the average for that group, okay? So means are less variable than individual observations. So that's really important. They're less variable, okay? The larger the sample size, the less variation we will see in the values of X bar. The larger the sample size, the less variation we'll see. So the standard deviation decreases as the sample size increases. Standard deviation decreases as sample size increases. So standard deviation, you guys, is going to be affected again by the sample size. From here on out, we will always take our standard deviation and divide it by our sample size. Before this, we never did that, right? We just, whatever standard deviation they gave us, we used. But now, from here on out, our standard deviation is going to be affected by that sample size. The larger the sample size, the smaller our standard deviation is. If the sample size is large, it will be approximately normal. I want to say in the book they use 40 in this chapter, and then all of a sudden they'll use 30. So somewhere we're going to say 30 is sufficiently large. Okay, 25 is not bad, but 30 is where we're going to cut it off. Okay, so, and we'll talk more about that when it comes up, but. Sample size is large, it will be approximately normal. So you guys, if you have 100, that's good. If you have we're talking about that sample size. Okay. It can never be perfectly normal because our data is discrete and normal distributions are continuous. That is from in the Flamingo book, it is from chapter 6. And in the blue book, it is from chapter 7. The mean of the sampling model will equal the true population mu. And the standard deviation is sigma over the square root of n. If the population is at least 10 times as large as the sample. Oh, that is the same way we use standard deviation on the other one, right? If the population is 10 times as large, so the population, it goes again for the standard deviation, greater than or equal to 10n, then we can use that standard deviation. They're the same for proportions. Standard deviation, how you can use standard deviation is the same. To prove normality, this is where it changes. It is called the CLT. You only use it with means, not proportions, with means. I am telling you use it with means, not proportions, never with proportions. If you write it with proportions, you are going to lose all credit. CLT, central limit theorem. CLT, central limit theorem always goes with means. If you have a mu, if you have X bar, you are to use the CLT. If you tell me P is greater than or equal to 10n, you miss it. It's wrong. That is not how you prove normality. From here on out, you never prove normality with means except with CLT. CLT! I need to get that in your head It doesn't go away. Not for the rest of the year. And I am telling you, the reason that the pomegranate lady comes out when CLT comes is because all of a sudden when we get to means or proportions, we write CLT for everything. Is there a P up there? Anywhere? Is there a P? Is there a P anywhere? No! There's no P because you can only use it with... Who said it? Who said it? Did you say P? Is there a P up there, Brandon?
No.
Do you use it with P's? No! You only use it with means. There's no P? So you only use it with means. CLT, only with means. It gets a little better when I don't have a mask on.
We can hear you, sorry.
Can you hear me? So when do you use it?
With P.
There are some things that are funny, that one's not. Because let me tell you, on a free response question, I am telling you right now, it comes to normality, you lose a point. A free response question is worth 4 points. You use the wrong formula, you use CLT for a P, you just lost a point. 1 point. Now you only have 3. If you're going to lose a point on a free response question, it should not be for this. Okay? I am telling you right now, CLT, and it really did because I would say, okay, we're going to use CLT. And everyone used it for P. And I'm like, there's not a P anywhere there. It's only used for means. The essential limit theorem states, if your sample size is sufficiently large, we're going with 30, right? Then you can say it is approximately normal. You have to. It is CLT. Do not use it with a P. I know, like, I make a joke because my dad used to do stupid stuff like that, and I'd be sitting at the test, and then I would start laughing because I would remember him doing stupid stuff, so you can take my dad. I do it because it's funny, gives you a good laugh. I do it also because it is a mistake, and I don't want you to make that mistake on the test. Because if you make it, you lose a point, and I want you to lose a point because for something big. To me, this is small, okay? Using the wrong parameter, using the wrong statistic, those are small things that you should not be losing points for. But on a free response question, those small things can add up. If you use the wrong parameter or you use the wrong statistic, you use CLT instead of N times P, or you use, like you mix it up, that's 2 points gone for 2 small errors. And you haven't even done the rest of the question. So I do go over the top with it. I didn't throw my temperature into quite as much as I used to. I usually shake my head, my hair moves and stuff. So I did stomp my feet. You guys missed it. So, but you guys got this, like I went out, okay? Do you think they heard me on the...
Well, it's still recording.
I know, I'm hoping.
Oh.
Yeah. They didn't get to see me though. And I can go back and edit it. Okay. So, the CLT states, if your sample size is large enough, sufficiently large, then your distribution is approximately normal. This is how you prove normality with means, okay? Normality with proportions, n times p, n times 1 minus p. For means, it's like this. And then the law of large numbers, we talked a little bit about this in the last unit, that draw observations at random from any population with mean mu. As the number of observations increases, the sample size mean gets closer and closer to mu.